Good day to all. Here, We Learners Note is an online platform to encourage a better way of education to all of our students. Here, I am Sarika Ma'am, your physics teacher. Let's start discuss our topic, that is capacitor and its effects. That is the effect of dielectrics on the capacitance of a capacitor. Let's start. So, a capacitor is an electric or electronic device used for storing electric charges. That is, if we have to store electric charges, we can use capacitors. This is the general representation. This is the practical view of a capacitor. Okay, so before going in detail, we have to know what is a capacitor. That is the structure of capacitor and how we can calculate the capacitance of a capacitor. Okay, so the basic structure of a capacitor, it consists of two parallel plates. The basic structure of a capacitor is a parallel plate. It will consist of two plates separated by a particular distance d. And A is the area of the plate. Okay, so here we can see that there are two plates separated by a particular distance d. Okay, and a battery is connected with the two plates of that capacitor. This battery is used for storing the charges on these two plates. Okay, so when we are connecting the positive terminal of the battery to one of the plate, that plate will be get charged with plus Q. That is, positive charges will be stored in that plate. Then the second plate is connected with the negative terminal of the battery. So the negative charges, that is the electrons, will be stored in this second plate. Okay, so this first plate is charged with plus Q charges and the second plate is charged with negative Q charges. Okay, here this Q represents the total number of charges in each of the plates. Okay, then this is the symbolical representation of a capacitor. We can represent a capacitor by using this symbol or this one. Okay, and this is the real view of a capacitor. In the discussion, I have told that a capacitor consists of two parallel plates. But in actual practice, the plates should not be in a plate form. It will be in the form of a paper. Okay, so the actual view, this is the real view of a capacitor. These two are the two parallel plates. They are in the form of sheets. They will be wounded on a common circular shape in a cylindrical shape structure. Okay, and this is the real view of a capacitor. Okay, then continue with our concept, that is we have to derive the expression for capacitance of a capacitor. We will represent the capacitance of a capacitor by using the letter capital C. C is the capacitance of a capacitor to store a particular quantity of charges. Okay, so for that, let's consider these two equations. That is, in plate 1, we have a charge density of sigma and the charge density is equal to Q divided by A. Okay, this Q means the total number of charges on the one of the plate and A is the area of that particular plate. Okay, so the charge density of the first plate is equal to Q divided by A. And the charge density of the second plate is equal to minus Q divided by A. Why this minus? Because this sigma is related with the charge density of the negative plate. Here we are substituting this negative sign here. Okay, then so we are going to derive the expression for capacitance of a capacitor. For that, we have to consider a capacitor having two plates separated by a distance d, and A is the area, and it consists of plus Q number of charges on the first plate and minus Q number of charges on the second plate. Okay, then here we can see that an electric field starts to flow from the positive plates to the negative plates. Okay, and for the derivation, we have to consider three regions: region 1, region 2 and region 3. And the region 1 and 2, region 1 includes the portion of the left side of this first plate and the right side of the second plate. And this region 3 also consists of this right side of the second plate and the left side of the first plate. For that, we have to consider a parallel plate capacitor separated by a distance small letter d, and A is the area of each plate. And here we can see that an electric field represented by the capital letter E. This electric field will be starts to flow from the positive charges towards the negative charges. And in order to derive the expression, we have to divide the area around this capacitor into 3. That is region 1, region 2 and region 3. The region 1 consists of the portion left side of this first plate and the right side of the second plate. And the region 3 is also the same portion, that is the right side of the second plate and the left side of the first plate constitute the third region. And the region 3 is in between the right side of this capacitor plate 1 and the left side of the capacitor plate 2. Okay, then next we have to find the total electric field relating to this region 1, 2 and 3. So we can see that in region 1 and in region 2, the total electric field strength is equal to 0, because from the picture we can see that in region 1 and this region, the direction of electric field is opposite. That is, here we can see that the electric field lines are going outward, because here we have positive charges. So electric field lines are going outward direction. And the second portion of this region 1 is the right side of this second plate. Relating to the second plate, the direction of electric field lines are inward direction. So combining these two regions, these two areas, we can see that the direction of electric field is opposite. So the total electric field relating to region 1 and similarly relating to region 3 will be equal to 0. Both of them will be cancelled. Then consider the region 2, that is region in between this area. Here the direction of the electric field lines are in one direction, in uniform direction, that is from top to down. That is, these electric field lines will be starts from this positive charges and ends in this negative charges. The field lines will be having the same direction. So the electric field relating to this portion, that is the right side of this upper, that is this first plate, and the left side of this second plate will not be cancelled. So what will be the total electric field relating to this region 2? It will be like this. We have to add these two values, that is sigma divided by 2 epsilon 0. Here we are considering these parallel plates as infinitely long plane plates. So relating to infinitely long parallel plates, the electric field strength is equal to sigma divided by 2 epsilon. Okay, so total electric field relating to the two regions of this plate is equal to sigma by 2 epsilon 0 plus sigma by 2 epsilon 0. That is will be equal to sigma by epsilon. Okay, so the total electric field relating to a capacitor plate is equal to E is equal to sigma divided by epsilon. Here sigma is the charge density and its value will be equal to Q divided by A. Q is the total number of charges of a plate and A is the area of that plate. Okay. Then next we are going to find the representation for potential difference between these two plates. We know that the potential difference is represented by the capital letter V. So we have V is equal to E into D. D is the distance between these two plates. We have to find the potential difference between these two plates. So V is equal to E into D. And we have the value of E as what? E is equal to sigma by epsilon 0. Okay, epsilon 0 or epsilon. This is the permittivity of that medium. Okay, so substituting the value of E here and D here, we will get the expression like this. Okay, E, in the place of E, we are substituting sigma by epsilon 0 and we are replacing this sigma by Q by A. So, sigma by epsilon 0 is replaced by Q by A epsilon 0. Okay, then D. This is the D, distance between these two plates. Okay, then we have another expression for capacitance of a capacitor as C is equal to Q by V. Then substituting the value of V here, we will get the final representation of capacitance as epsilon 0 A by D. This is the final representation of a capacitor without dielectric. Next, we are going to discuss about the effect of a dielectric on the capacitance of a capacitor. Okay, so for that we have to know what is a dielectric. Okay, effects of dielectrics on capacitance. Okay, dielectric is actually an insulator at normal condition. It is a non-conducting material at normal condition, but it is not actually an insulator, but it will be behave as an insulator at the normal condition. Okay, so in a dielectric type materials, the positive and negative charges will be in the form of neutralized condition. They are inactive. We cannot get the presence of positive or negative charges in that type of the materials. So what will be happen if we are applying a voltage on the two sides of a dielectric? What will be happen? We know that in a dielectric, the positive and negative charges are in a joined condition. They are in a neutralized condition. So when we are applying a voltage, these two charges, that is this positive and negative charges, will get separated. They will get a dipole moment. They will form a dipole, temporary dipoles. Okay, so there will be positive and negative charges in that dielectric if you are applying a voltage on the two sides of that dielectric. Okay, and if you are placing a dielectric material in between the two plates of a capacitor, the same thing will be happen there. Okay, so what will be happen? The dielectric will become a conductor. That means it will be having a separated positive and negative charges. Okay, then what will be happen? Here, this is a representation of a dielectric in which we have applied a voltage on two sides of this dielectric material. By the application of this voltage, the dielectric become a dipole, temporary dipole material. Here we can see that the positive and negative charges are separated by a particular distance. That is the dipole condition. Okay, so what will be happen in this condition? Here we can see that this positive charge and this negative charge, and this positive and this negative, and like this positive and this negative. All these positive and negative charges of the neighboring dipoles will be joined together. They will be get neutralized again. So what will be happen in this area, that is here. Here there is no effect of positive and negative charges. Okay, there won't be any presence of positive or negative charges because they get neutralized. Then finally what will be happen? We can see that here in this portion there is negative charges, and in this portion here it is positive charges. Okay, there is a number of negative charges on this side and a number of positive charges on this side. So these two charges on opposite side does not have any other opposite charges to get neutralized. So they will remain as it is. Okay, and we can represent the charge density of these negative charges as minus of sigma p. Okay, and here the charge density of this number of positive charges as sigma p, positive sigma p. Okay, and if we are placing a dielectric having a behavior like this in between the two plates of a capacitor, what will be happen to the capacitance value? Let's check. Here we got the expression of capacitance of a capacitor as C is equal to Q divided by V. Okay, here I am using this C0 and V0. The 0 notation is for representing the initial values of capacitance. Okay, next we are going to discuss what will be happen if we are placing this dielectric. Okay, now we can see that in this condition, that is if you are placing this dielectric, what will be happen? The charge density on the positive plate of that capacitor will be changed from sigma to sigma minus sigma p. Okay, because we can see that here this is the positive plate and this is the negative plate, and this positive plate has a charge density of sigma and negative plate has a charge density of minus sigma, and here we are placing a dielectric in between them. Okay, and this dielectric have a negative charge density on this left side, that is negative sigma p, and this side the same dielectric have a charge density of positive sigma p. So due to the presence of these charge densities, the total charge density on the positive portion, this portion on the positive plate, okay, and the total charge density on the negative plate of this capacitor will get changed. How much it will be changed? The effective total charge density of this positive plate will become sigma minus sigma p, that is charge density get decreased. On the right side, that is on the negative plate of the capacitor, the charge density become like this. So here also the charge density get decreased. Okay, so this decrease of charge density, how it will affect the capacitance of the capacitor? Okay, for that we have to come to the same equation, that is E is equal to sigma by epsilon 0. Here this sigma is changed to sigma minus sigma p, because this is the new charge density of one of the plate. And we have expression for electrical potential, that is the potential difference between the two plates of a capacitor, as V is equal to E into D. And here we have the expression for E as sigma minus sigma p divided by epsilon 0. Substituting this value, we will get V is equal to sigma minus sigma p divided by epsilon 0 into D. Okay. Here we are going to make some approximations in our equation. That is, we are approximating the term sigma minus sigma p is equal to sigma by k, small letter k. Here this k indicates the characteristics of a dielectric. It is a constant value. Depending upon the type of dielectric material, the small letter k value will be changes. Okay, then substitute this value in our equation, that is in the previous one we have the expression of electric field is equal to sigma minus sigma p divided by epsilon 0. Here we are replacing this sigma minus sigma p by sigma by k. So our equation will become like this. And again we are replacing this sigma with q by a. Okay, because we have the expression of charge density sigma is equal to q by a. So our equation will become q d divided by a into epsilon 0 k. Here we are going to approximate the expression, that is we are making some substitutions. K is equal to, capital K is equal to epsilon divided by epsilon 0. And if we are multiplying this epsilon 0 with this k, we will get an expression as k into epsilon 0 is equal to epsilon. That is the permittivity of the medium. Permittivity means that how much that medium permits the flow of charges through them. It depends upon the type of the medium. It depends upon the type of the materials we are using as dielectrics. Okay, then our equation for capacitance will become C is equal to Q by V, and substitute the value of V from here. We will get the final expression of capacitance of a capacitor as A into epsilon divided by D. Okay, then in the previous step you can see that there is a term K here. That is the term K indicating that the capacitance, depending upon the value of the K, the capacitance of that capacitor will be increases. That is, if we substitute or if we are placing a dielectric in between the two plates of a capacitor, the capacitance increases by a quantity K. Okay, like this. Okay, so from this equation we can see that C is equal to capital K into C0. K is the permittivity of that dielectric and C0 is the initial capacitance of that capacitor. So we can see that the capacitance can be increased by placing a dielectric in between the two plates of a capacitor. So here I am concluding that our capacitor is a charge storing device, and we can increase the capacitance of a capacitor by inserting a proper dielectric in between the two plates of that capacitor. Okay, so dielectrics are used for increasing the capacitance of a capacitor by a value K. Dear students, I hope all of you understood the topic that we have discussed on today. We have a lot of videos relating to our topic, and you can see that from our official website, that is www.learnersnote.com. Here I am Sarika Ma'am, your physics teacher, signing off.